Good evening. Welcome to class. Tonight, we're going to, first of all, do a bit of housekeeping here as far as just some navigation things that I want to kind of show out to everyone on the capacitor. And then we're going to have some teaching time that's going to be on load calculation. So you're going to want to have your code book ready for you. And that's really what our intent is moving forward with these classes that we periodically have these meetings and provide some additional instruction, expanding on some instruction and that sort of thing. So just to get into the housekeeping thing here first, I wanted to show you guys some things that on capacitor that you may or may not be aware of. And I know some of you may be transplants from other programs. Some of you may be have been with us for a few years. So just wanted to show you this. Looking at my desktop looks a little different than yours because I have every class in Kentucky that shows up on it. But if you, let's see. Well, if you look over here in review material, that is where you will find all of this stuff. We'll be camping out here a lot in 2023 exam prep. And first of all, let me say, while I'm thinking about it, I'm going to page down here towards the bottom. Understanding electrical estimating. There is understanding electrical estimating, and then there's electrical estimating, the second edition. The version that you have is understanding electrical estimating. There's been some confusion on that, but just wanted to point that out. So, but back up here to 2023 exam prep. You'll notice that it says book. So the entire book is on here in electronic form. So if you didn't have your books available to you, you can actually see the book on here without having the book physically in hand. Maybe you're on a job site or at lunch or whatever, wanted to look something up or work on something remotely. You also have presentations, and that is something that you didn't have until a couple of days ago. And I mean, some of you guys that have been in the program a while may have not have had that. I talked to Ryan Carlson with My Cold Enterprises, and they just added that for us in the last couple of days because I wanted you to have the PowerPoints to have available to you. And I will be using those periodically, just depending on the subject matter that we're using. There's also videos, and of course, as many of you know, in the homework there is a tab that you can click on a video, and there'll be an expanded teaching on any given subject. And then, of course, you have the questions to answer, but also just trying to provide as many resources as possible for you to have to make sure that you get the bang for your buck that you want. So tonight I'm gonna kind of veer off of the grid here, though, and I'm gonna use a different resource other than capacitor. You guys being fourth year students and being in the position you're in, getting to the end of your education, I guess you would say, wanted to take opportunity to expand on some things and talk about load calculations. So first of all, before I even get into that, I wanted to ask if you have passed or let's say if you need to pass your licensing exam, if you would, up there at the top, I think your screen is the same as mine. The one that says raise your hand, click on that. I want to know how many people need to pass their licensing exam that are in the meeting. If you would do that, please. All of you are licensed? Oh, okay, I got one, Andrew. All right. Joshua, okay. All right. Yeah, and I knew that I had some guys in here that already passed their exam. And first of all, let me say this: some of the material throughout the fourth year is, I think, some who may have gotten to the fourth year and they've already passed their exam, they might be looking at it as it's child's play. I don't need to talk about that. Yeah, you do. And we're going to expand on some of that as best we can because some of you, if you pass your exam, according to Kentucky state law, you can take the exam and after second year, and if you got 4,000 hours of OJTs and you pass the exam, you can get an EE level license in Kentucky. that does not mean that there's not more education to be gleaned from all of this. And as you can see from the screen that I'm showing here, load calculating, that is a primary suspect as far as information that individuals like yourself need to know and have be savvy about in the field. So I'm going to take some time to go through some things. I don't know that I'll be able to get through all of what's on this PowerPoint tonight or not. We'll just have to see. But as we move forward, well, first of all, there's a lot more people in this class than is actually in this Teams meeting tonight. I can tell you that. Um, so if you know of anybody who actually is a part of this and doesn't get in the meetings, please encourage them to get into the meetings because we have a schedule to hit throughout this year that is several meetings throughout the year, and I intend for them to be meaningful. The some of the teaching that you're going through as you guys are working through the assignments. First of all, if you haven't started on your assignments, you need to get on it. Don't get behind. Um, and the first two segments in this is estimating and then leadership. Both of those are great subjects. I don't really intend to do any teaching on estimating in these Zoom meetings, but on leadership or estimating, I do intend to talk directly about the code, talk about some upcoming changes in the code. As we move forward, I'll end up doing some stuff, I'm sure, especially with you guys on the 2026 changes because looking around, this is on the way. This is not the code book, but this is the IAEI's or the International Alliance for the Electrical Industries analysis of the 2026 changes. Whether you've passed your exam yet or not, the changes are coming. And I don't know where all you guys are. I know we got some local people on there because I know some of you guys, but we have in Kentucky, we just adopted the 2023. I'm not sure what they're going to do about the 2026. And buddy, there's some big changes in there. Also, I'm in New Albany, Indiana, just so you know, which is about 5 miles from Louisville. And in Indiana, they have not adopted a new code cycle for a really long time, but they are actually, it's going before a board of whoever at the state level, and there's a very good possibility they're going to be adopting the 2023. They're going to go through and say, yeah, but we don't like this and we don't like that. They're going to kind of slice and dice it just like Kentucky did. But that's all important stuff for you guys to know. And generally, speaking, the 2023 changes is what I will spend some time teaching on throughout the year with you guys to get you up to snuff with not only just knowing the code, but knowing what those changes are. Because we are in a code cycle. I don't care where you are, if you're in Ottumwa, Iowa, or if you're in Florida or Texas or where you are, that's going to affect nationwide where you are, especially because a lot of you guys are in this class because you work for a company that may have a travel base and you might not be working in the same state all the time. So, that being said, we want to teach the most recent code. And as things develop, here in the coming weeks, I will have PowerPoints that have to do with those changes. And we want to make sure everybody's up to snuff on that. So before I kind of get into my teaching here, is there, and this is a grenade of a question. Is there anyone in this group right now that doesn't have their books? Andrew, you don't have your books?
Is it okay if I talk?
Yeah, go right ahead.
Yeah. I got into the class kind of late, so I'm pretty sure I'm getting my books, but it's just my responsibility. I didn't enroll in the class in time, so that's probably the reason why. But I'm pretty sure I'm gonna get my books in.
Who are you with? What company?
Gaylor Electric.
Okay. Okay. And Andrew Meckel, are you one that don't have your books too?
No, I have my books. I just can't figure out how to stop hitting this little hand up thing. I've got all my books.
Great. Hey, and I'll be the first one to say I'm no expert on Teams meetings, but I got it to work.
I might hit it a few more times before class is over.
All right, no sweat. Okay, So everybody else, if there's anybody else needs to tell me, I want to know where we're at on books, because that, that is that is a mountain to climb every year about this time for me to get books out to everybody across the land, because we have people all across the East Coast that are in these classes, and it might be a set of books I got to get just across town, and it might be from here to Texas. So hopefully you guys have all got them squared away. I think we still got a couple stragglers out there in maybe the other classes, but I kind of thought I had everybody taken care of in here. So very good. So going to talk about load calculating tonight, and I'll be very respectful of your time. These, just so you know, these meetings would typically last probably about an hour, unless we got into questions or something like that. That's really what I'm looking at for them to be. So load calculations. For the electrician, the key element for installing electrical systems is amperes. That's the piece that we need in order to be able to build the job. Once this component has been established, the install design work can begin. So these are all the subjects, and like I said, if I were to get through all of these, it'd be a wonder, but we'll see. Branch circuit calculations, general lighting loads, fixed appliance loads, cooking equipment loads, voltage drop, motor calculations, and commercial load calculations. And I'll actually, to be honest with you, I'll put this presentation together to teach in my CEU classes, or continuing education classes. And I have yet to get to teach it because I'm teaching on the 2020 and 23 changes in the code classes. And because that's the last look. Next year I'll be teaching the 26, and I've yet to get to this. And I think this presentation really is kind of like a teaspoon of all of this. Not the deep dive or anything. We may get more into that later in the year. So, branch circuit load calculations. And if you see these screenshots that I've got in here, this is actually from what's called NFPA Link. Kind of a cool thing about NFPA is that on their site, they have what's called NFPA Link. And like in 2017, they let you, you could actually download the 2017 NEC directly off their website, the whole book, and have it as an icon on your desktop. I did it with all my teachers in Kentucky, and it was like free code book, and you could pull it up on the screen and see it. Well, I guess they quickly figured out maybe that wasn't a good idea for them. And they started what's called NFPA Link. And for $11 a month, you can actually have access to any code, I believe it is, that the NFPA has. Which also means that, like the handbook, the great big code book, that you basically get a version of that on here. So, and that's what a lot of this comes from. So anyway, 220.11 maximum load. Motor operated combination loads. Let me start with the first sentence there. Total load on branch circuit shall not exceed the rating of the branch circuit nor the maximum loads specified in 220.11a. So where a circuit supplies only motor operated loads, the conductor sizing requirement specified in 430.22, which is talking about single motors, shall apply. Where a circuit supplies only air conditioning equipment, refrigerating equipment, or both, the requirements are from 440.6. You should know 430 is certainly motors and motor control. 440 is going to be air conditioning and refrigeration equipment. For circuits supplying loads consisting of a motor operating utilization equipment that is fastened in place and has a motor larger than an 1/8 horsepower in combination with other loads, the total load shall be based on 125% of the largest motor load plus the sum of the other loads. One thing to remember about calculating motor loads, you're pretty much always going to calculate it at 125%. If you have multiple loads, you're going to calculate it at 125% plus the additional motor loads, which I believe comes up in this. Inductive and LED lighting loads. For circuits supplying lighting units that have ballast, transformers, auto transformers, or LED drivers, the calculated load shall be based on the total ampere ratings of such units and not on the total watts of the lamps. The classic statement in teaching is that when you're calculating loads, for example, with fluorescent fixtures have ballast in them, of course. When you're calculating the load for a room full of fluorescent fixtures, and it's not impossible, you would still do that, I guess, something existing, you calculate that based on the ampacity given on the nameplate of the ballast, not by the wattage of the bulbs. Receptacle outlets. Except as covered in 220.41 and 220.14J, receptacle outlets shall be calculated at not less than 180 volt amperes for each single or for each multiple receptacle on one yoke. A single piece of equipment consisting of a multiple receptacle comprised of 4 or more receptacles shall be calculated at not less than 90 volt amperes per receptacle. So 220.47 contains demand factors that apply to the load calculation in 220.14H. And in dwelling units, the minimum unit load for receptacles supplied by general purpose branch circuits is specified in 220.41 and based on the floor area. Essentially this, if you're calculating in a commercial application per receptacle, general purpose receptacles, you're calculating those at 180 VA. And of course, if they're continuous duty receptacles for any reason, then it would be at 125%, which that's going to be 225 VA. Now, and I'm probably jumping ahead on my own presentation here, but when you're calculating for a residential single-family dwelling load, when you're doing that dwelling unit calculation, when you do the very first thing in that calculation, which is taking the square footage of the dwelling unit, say it's a 1,000 square foot home, you take that times 3 volt amperes per square foot, so that's 3,000 VA. That number right there covers all the general purpose plugs, you know, the plugs in the living room, the plugs in the bedroom and stuff like that, and all of the lighting load is covered in that particular line right there. That would be 3,000 VA. If you're calculating in a commercial load, then it is 180 volt amperes per outlet. Fun fact, which I've learned in my brand new book, 2026 Changes, that 3 volt amperes, that multiplier of 3 volt amperes per square foot, in the 2026, they have changed it to 2 volt amperes. Reason being, the advancement of LED lighting, the reduction in the loads. You know, if you get into something else that's being pushed in the NEC now is copper-clad aluminum. The aluminum industry is trying to get back in the game after their debacle in the 1960s and 70s. But they have now kind of starting to push copper-clad aluminum. But I mean, on a 14 gauge, 14.2 copper-clad aluminum Romex, the maximum load you can put on it is 10 amps. But my point being is this: the loads that you're seeing in a single-family dwelling now for lighting have come down dramatically. So it's kind of where that comes from. So here we go. I don't think I got my screen large enough here for this. In dwelling units, the minimum unit load for receptacles supplied by general purpose branch circuits is specified in 220.41 and based on the floor area. The following exhibit, I'm kind of skipping around here, shows the load of 180 VA applied to single and multiple receptacles mounted on a single yoke or strap, and the load of 360 VA applied to the outlet containing 2 duplex receptacles and to the outlet containing the device with 4 receptacles. So they kind of give you a breakdown. You know, single outlet, still 180 VA, duplex, 180 VA, triplex, don't know how many of those you're putting in these days, 180 VA, and then a fourplex is what I call it, 360. And then we've got this down here, the kind of another fourplex, I guess you'd say, at 360. And here they kind of give a breakdown of that. So, I feel like my screen is not large enough for you guys to see the top part of this. In the exhibit below, the maximum number of receptacle outlets permitted for 15 amp branch circuits is 10 and 13 outlets, 15 and 20 amp circuits, respectively, based on the load assigned for each outlet by 220.14. This restriction does not apply to receptacle outlets in dwelling occupancies. And the reason I make a big deal out of that is because that's a classic journey level exam test question, and that is what is the per outlet calculation for a receptacle in a single family dwelling? Well, that's a trick. That's all done in that first part of the calculation to determine the total load for a dwelling unit. But here they're saying 10 outlets on a 15 amp circuit, 13 outlets on a 20 amp circuit. I don't know. Yeah, I don't think it's in my thing here to do that calculation. But when I first started in the trade, how I was taught to determine how many receptacles I would put on a circuit was 15 amp circuit, 8 plugs, Mike. 20 amp circuit, 10. No calculation, just what we call rule of thumb. Well, if you do this calculation and you go, okay, a 20 amp, 120 volt circuit, how many, you know, what level of load will that actually take? Well, 20, straight from the power wheel, 20 times 120 volts is 2,400 watts. So if you take the 180 VA factor, 2,400 divided by 180 VA, that will give you 13.3 receptacles per that circuit. Now you're going to round off that 3, so that means you can put 13 receptacles on a 20 amp circuit. That's where that comes from. And I mean, I was in the trade for a fair amount of time before I really even knew why. Somebody just said, you do this and you're okay. And quite frankly, that's what I was told when I was calculating, how many lights do I put on a circuit? 10 things. Don't count switches because there's no load there. 10 lights. Well, today, if you do the calculation and go based on that, you would really be leaving a lot of room on the circuit. Now you should be able to get more than that because of the decreased lighting load in really any application, where it's residential or commercial. So Article 220, branch circuit feeder and service load calculations. This one I could spend the night on, I'm sure, but we'll just do a little quick tour through it. So this is what I was talking about just a moment ago. You have in the very first part of the calculation for a dwelling unit, and by the way, I know many of you guys are doing commercial, industrial work. You may not be doing residential, but still need to know this, especially if you're still, queuing up to take your exam. That exam is for the residential, the commercial, and the industrial guys. It's not one sector. So, for example, here you have from Article 220.41, 3 volt amperes per square foot. That's changing. But let's say we got a 2,500 square foot house times 3 volt amperes. That's 7,500 VA. The lighting and the general purpose receptacle load is determined in that line alone. Small appliances, those are calculated at 1,500 VA each. So you got 2 of those, so 3,000. Laundry circuits are 1,500 VA, so that's 1,500. You got 1 of those. Add all those together, that's 12,000 VA. Then you take, with the total from line 4, look at table 220.45, you take the first 3,000 at 100%, so we're going to subtract that, which leaves us 9,000. Then beyond that, you have to calculate it at a 35%, and that gives you 3,150. Add the 3,000 back in. Your total general lighting load for this 2,500 square foot house is 6,150 VA. Now again, you might be thinking, if you're not doing residential wiring, what do I need to know that for? Well, if you get into commercial calculations and hold that thought, you'll see the variances, but there's a great deal of the same type of thing happening. This is a great way to start out. And if you're taking your journeyman's exam, you may not get a calculation that says, determine the size service I've put on this house, but you might get general lighting load, you might get fixed appliances and some other things, just the different pieces of it. So here's fixed appliances. And let's say we have a range or cooking equipment. If you have if you have a piece of cooking equipment, you got a full standing range that is 12 kW or less, it's automatically calculated at 8 kW or 8,000 VA. Electric clothes dryers are calculated at 5,000 VA or the nameplate rating, whichever is greater. I can't remember if I included it in this presentation also, but something that's been added, and I believe that was added in the 2023, maybe the 2020, and that is that calculating a load, whether you put one in or not, calculating the load for a electric vehicle charger. Those are calculated at 7,200 VA, which is basically 7,200 VA at 240 volts is a 30 amp circuit. So here we have our clothes dryer at 5,000, and then we have 4 fixed appliances in addition to that. If you have 4 or more fixed appliances, you can derate those. So we take the dishwasher, the air compressor, the deep freeze, and the hot tub, add all those together, that's 22,000 VA, and we can multiply that by 75%, that gives us 16,500. Add the 8,000, the 5,000, and the 16,500, that gives us the total fixed appliance load at 29,500. Now notice, you take that, and then on the very last line there, you see it says add lines 7 and 11. You take the general lighting load and the fixed appliances, that would give you 35,650 watts. What I'm doing is I'm using a form that I have created that is how to calculate the dwelling unit total load. And we'll probably do that at some point. It's a great exercise to see how these different loads break out. Now here is if you have a calculation for a cooking piece of equipment that is more than 12 kW. If it's 12 kW or less, it's automatically calculated at 8 kW. More than 12 kW, here's what you do. So we're saying we've got a load here that is 16 kW. There's the example to the right. 16 kW minus 12 is 4. 4 kW times 5% gives you 0.2. And 0.2 times 8 kW is 1.6 kW. And then 1.6 kW plus 8 kW gives you 9.6 or 9600 VA. So if you had a load at 16 kW, that would be your actual amount that you would use for your calculation. And if you have a kitchen that has, full standing range, and that's what it is, then there's your calculation. If you have multiple appliances, let's say you've got a cooktop and then you also have a double oven over here. If they're all in the same kitchen, you can add the kW load of all of those together and then calculate them just like I've shown you as a single appliance, you might say. Now let's say you've got a house that has maybe a kitchen in the basement, in the man cave, or you got a mother-in-law suite, bless your heart. But anyway, if you got a mother-in-law suite and you got a second kitchen, then you would calculate those differently. But if they're all in the same room, there you go. Let's see, Article 210, voltage drop. One of the most misunderstood things or neglected things, I think, in our trade. What I believe are the most things that are neglected the most is box fill, voltage drop, and really grounding and bonding. So minimum ampacity, 210.19 conductors. This is where it speaks specifically as to voltage drop. And it says branch circuit conductors for circuits not exceeding 1,000 volts AC or 1,500 volts DC shall be sized in accordance with 210.19A through D. And then it says, booyah, informational note. You should know by now as a fourth-year student that an informational note in the NEC is what is termed as not enforceable code. It's a suggestion. When it says shall and shall not, that is enforceable code. Informational note, conductors for branch circuits as defined in Article 100, sized to prevent a voltage drop exceeding 3% at the farthest outlet of power, heating, and lighting loads or combination of loads, and where the maximum total voltage drop on both feeders and branch circuits to the farthest outlet does not exceed 5%, provide reasonable efficiency. So in other words, 3% for branch circuits, but if you're dealing with the branch circuits and the feeders themselves also, that doesn't double, it's 5% for the branch circuits and the feeders. So down here at the bottom it says, excessive voltage drop in supply conductors can cause inefficient operation or malfunction of electrical equipment. Under voltage conditions reduce the capability and reliability of motors, lighting sources, heaters, and solid-state equipment. It may be necessary to compensate for this with an installation beyond the minimum requirements. The problem is that if you are not considering voltage drop in your installation, the problem ain't going to show up until after you fire it up. I mean, and I had somebody in one of my classes once, a code class, I was teaching on this, and they said, yeah, we did that. That's exactly what happened. But let's say you put in power out to a motor on a gate that's 400 feet away from the power supply. And, you hook it up, probably going to work, but the voltage drop is excessive. That motor may run for a while, but it will prematurely burn out. And then, now what are you going to do? You've ran this line underground all the way out there 400 feet. You size the pipe for that size conductor, and the pipe's not big enough to put the right size conductor in it. That's a big problem, isn't it? That problem isn't going to show up until after you've installed it. When is the tip point? Well, if you do the calculations, for example, just in installing a circuit inside of a commercial building, let's say it's anything over 200 feet, I'd be starting to be concerned about it. Depending on what's on the circuit, of course. But anything above 200 feet, you can start beginning to have enough voltage drop that it's a concern. Whenever I'm pulling wire, I'm going to think about, okay, I know this run is pretty long. I'm going to start with a fresh roll if I'm pulling off of 250-foot coils or MC cable or NM cable, whatever. I'm going to start with a 250-foot coil so I can monitor how much I'm putting in. And there is the classic calculation. Voltage drop equals 2, which 2 means the distance out and back. K is the constant, which, where do you get the constant at? I mean, there's a whole way to calculate that, but the constant is, it's 12.9 for copper and 21.2 for aluminum. And it's in the Uglies book, which you need to have an Uglies book. You can use that to take your exam, by the way. And it's listed in here. There's a way to actually calculate that, but if I'm working in the field and I got a voltage drop calculation I need to do, this is the formula I'm doing. I don't think I even dealt with in this presentation that there's the other method that some of you have probably already seen, and that is where you're using the resistance per 1,000 feet. If you do one and then do it, I was doing this literally in class today. You do one and then do this calculation here, it's going to be extremely close. They won't be exact. Sometimes maybe they are, but it's going to be extremely close. The K is the constant times I, which is your ampacity, times the length, divided by the circular mill area, which is found in Chapter 9, Table 8. I believe, I put in here the three-phase version of it too. So 1.732, which we all know is the square root of 3 for three-phase. That previous one, that's for 2, which is the distance out and back. This one, if you got a three-phase circuit and you're installing in this application, 1.732 times K times I times L divided by circular mill area from Chapter 9, Table 8. Reasonable operating efficiency is achieved if the voltage drop of a feeder or branch circuit is limited to 3%. That's generally speaking what the case is. If let's say you're doing work in a plant like you see in the picture here, and you have a piece of equipment that is, might be European, maybe it may have a manufacturer tolerance rating that says we can't have a voltage drop on this piece of equipment that's more than 1.5% or 2% or something like that, then you might have to consider that. And I have ran into that before myself. However, the voltage drop of a branch circuit plus a feeder can reach 5% and still achieve reasonable operating efficiency, generally speaking. The voltage drop value is explanatory material and as such appears as an informational note, and the informational notes covering voltage drop are not mandatory. Which has always been something I thought was interesting about the code. Induction motors would run, if you have voltage drop, induction motors would run hotter and produce less torque. Well, that's not good. With an applied voltage rating of 10% below rating, the running current would increase 11%, and the operating temperature would increase 12%. At the same time, torque would be reduced 19%. Well, that's probably not what you wanted. Okay, doing good on time here. We're going to jump into Article 430, motors. So let's talk about motors and motor circuits. So again, under 430.22, single motors, we kind of started out with that. Conductors that supply a single motor used in continuous duty application is going to be multiplied by 125% without reading that whole spiel. The big thing to remember about motors, and I think I probably did this in my presentation, I can't remember if I did or not. When you're calculating this, you're going to use 125%. This is for short circuit and ground fault protection, overcurrent protection, and sizing conductors. You size them from the NEC. The FLC comes from the NEC. If you're sizing overloads, that is going to come from the nameplate rating. You do not go to the motor and look at the nameplate rating and go, 20 amps, and then you size your overcurrent protection based on that. That would be incorrect. So 430.6, and we have the size of conductors, supply, and equipment covered by this article shall be selected from the ampacities in 310.15, or shall be calculated by 310.14, where flexible cord is used. General motor applications down here in the tables. Other than for motors built for low speeds or high torques and for multi-speeds, the values given in 247, 248, 49, and 50, all of your tables in your code book that are dealing with the ampacity of motors, is where this is coming from. So, not to be used to size branch circuit conductors for continuous duty motors. That's a nice little caveat too. other than continuous duty. So conductors for a motor used in a short time, intermittent, periodic, or varying duty application shall have an ampacity of not less than the percentage of the motor nameplate current rating shown in table 430.22e. There's the yeah but. So 430.22e. This motor is a continuous duty motor, and this rule would not apply. Now, 24, conductors supplying several motors. So you have a single motor at 430.22. You also have 430.24 if you have several motors or motors and other loads. Conductors supplying these shall have an ampacity not less than the sum of the following: 125% of the FLC rating of the highest rated motor as determined in 430.6, and the sum of the full load current ratings of all the other motors in the group as determined by 430.6a. So you would take the highest level motor and then and multiply it by 125%, and then add the FLC of the other motors together. That would give you your calculation. Commercial load calculations. Okay, so first of all, organization of Article 220. I don't know if you guys can see the top of the screen here or not. Whoops. But it says Article 220. First of all, let me drop this grenade. Article 220 in the 2026 National Electrical Code is Article 120. You know, I think I'd mentioned it maybe in our orientation that they are rearranging the code book. The 2023 was a step towards that. The 2026 is yet another step. By the 2029, the organization of the National Electrical Code will be quite a bit different. Many articles will be moved around. You know, that's something, as more information comes out, I'll have PowerPoints probably here sometime in the next couple of weeks that will be all about the 2026. And we'll begin to talk about that as that unveils itself. But yeah, that's a big change. That's why I was really encouraging anyone that still hasn't taken their licensing exam. I would be doing it as soon as appropriate or as possible, because let's face it, it's hard to tell, whatever state you're in, or Kentucky or Indiana, exactly when they're going to adopt. But when they do, I would hate to say you're all queuing up, getting ready to actually take your exam, and then they decide they're going to adopt the 2026 and it's a rearranged code book. That's definitely going to increase the difficulty exponentially. So this is really just showing the organization of it, and there's a few different articles like this that have this, the organization of it in the front of the at the charge statement of the article. So this is showing part 1 is just general. Part 2 is branch circuit load calculations, huge part. Feeder and service load calculations in part 3. 220.61 neutral loads, and then part 4 is optional feeder and service load calculations. Part 6 is marinas, boatyards, and docking facilities. So, got a little example here. What's the general lighting demand load for a 100,000 square foot office building? Well, an office building is calculated at 1.3 volt amperes per square foot. And that's table 220.42a. So 100,000 square foot times 1.30 VA is 130,000 VA lighting demand load. For feeder service conductor sizing, what's the demand load for 100, 15 or 20 amp, 125 volt duplex receptacles in a non-dwelling occupancy after applying 220.47 demand factors? Well, let's see what that is. So you got 100 receptacles calculated at 180 VA. So that's 18,000 VA connected load. Under 220.42, I believe it is, you take the first 10,000 at 100%. So you're going to subtract that first 10,000. And then the remainder is calculated at 50%. So 8,000 VA is going to be, at 50% is going to be 4,000. Put that 10,000 back in there. Your actual calculated load for that is going to be 14,000 VA. Air conditioning versus heating load. This is demand load for 220.60. That's what's called non-coincidental loads. In other words, that thermostat in your house will not do heating and AC at the same time. So if the air conditioning motor is the largest motor in the question, then when calculating the air conditioning load of a multi-motor hermetic refrigerant motor compressor, compare 125% of the nameplate marked rated load current of the air conditioning load in VA to 100% of the VA of the fixed electric space heating load. Use the larger of the 125% of the air conditioning load versus 100% of the electric heating load. So here's our example. What's the service demand load for a building with a hermetic motor compressor driven AC unit rated as 16.70 amps as compared to a 6 kW heat? The system voltage, of course, is 12240 single phase. So 240 volts times 16.70 amps. The VA would be 4008. The 4008 times 125%. So that's 5010 VA. So we're going to omit this one because 6 kW at 240 volts, that's 6000 kW or 6000 VA. So that is the larger of the loads. And what you do is take the larger of the two loads, because they're non-coincidental, because they're not going to run at the same time. Take the larger of the two loads, use that as part of your calculation, and the other load is omitted because you'd never run those two loads at the same time. And grounding electroconductors. What size grounding electroconductor is required for a service supplied with two sets of 300 kc mil conductors in parallel? That's going to be taking from 250.66, which I'll jump over there real quick. 250.66 in your code book. Which is size of the largest ungrounded conductor or equivalent area of the parallel conductors. See what I'm saying? You're gonna take the equivalent area of those conductors. So 300 kc mil times 2 raceways gives you 600 kc mil. That's going to be a 1-aught grounding electroconductor. And the largest grounding electroconductor required to a ground rod is 6 AWG, by the way. And the largest to a concrete encased electrode or OOFER ground is number 4. Okay. A couple more things and I'll wrap it up. Appreciate you guys staying with me. What size service conductor in amperes is required for a lighting industrial manufacturing building with the following loads? Lighting at 20,000 VA at 277, 150 20 amp at 120 volts, 5 welders, non-motor generator, arc type, 50 amp and 40 volts, 50% cycle, a lot of pieces here. Air compressor at 10 horsepower, grinder, 2 horsepower, and 3 continuous use industrial process dryers at 10 kVA. You know, calculation like this, is, to be honest with you, is probably going to be on a master's exam. You know, and sometimes we have, some of you guys may know this, I don't know, but, you know, if you are taking your journey level exam, you can take the master's exam. And then if you don't have the hours to get the master's, of course, you can go ahead and get the journey level license, at least in Kentucky. And then once you've achieved the appropriate amount of hours for your master's, you can go back in and say, okay, I would like to upgrade my license now that I have achieved the amount of hours to be rewarded or awarded the master's. So determine the non-continuous loads and motor loads. 22 receptacles times 180, 3960. And then we have each welders at 480 volts times 23 amps at 78% is 8611. And then we're taking all of these, adding them together, getting our welder demand load at 24,542. So here's our air compressors, our grinders. Taking all of that load, determining it at 480 volts, for example, with the grinder times 3 amps times a 1.732 gives you 2490. Total non-continuous loads and motor loads at 38,860. By the way, instead of reading all this math to you, I do want to mention that this is recorded, and I'll send out a link to everybody in the class so you can go back through these. This, of course, is all in the, this particular stuff is in the exam prep material. So bringing it all down to our total VA divided by E times 1.732 gives you a total load of 132 amps. Note the conductor and overcurrent protection is as follows. The overcurrent protection device is at 150, which is coming from 240.6A, your standard ampere ratings for inverse time and circuit breakers. Always good to review these important calculations, and what I like to say is do the calculation before the installation, or suffer the consequences. Okay? All right. So does anybody got any questions for me at this point in the day? So I believe our next meeting, let me check my schedule, is on the 23rd, it looks like, of October. I think there's a little bit more of a window than I'd like to have on this next one, but I think we're going into fall break, and I'm actually on vacation. I think that first week in October, so we're back on the 23rd. Hopefully everybody does have my email. If you have any questions or concerns, you're more than welcome to email me and ask, or if you have any questions about any of the material, that's what my job is. I'm your resource, so I'll be sure and ask that. As we move forward here, we're going to talk about licensing exam. We're going to talk about the 2026 changes. We'll talk about the 2020 and 23 changes, because those of you, depending on where you are, in Kentucky, they did not adopt the 2020. They went straight from the 17 to the 23. So knowing what those changes are in the midst of all that is very important, because we're going to be looking at the 26. So if you were working, for example, as an electrician in Kentucky, you would not have a requirement of the 2020 changes during that cycle, but now you do. If you are an Indiana electrician, we're getting ready to adopt the 23. If you haven't been making a study of the previous code cycles or the most recent code cycles, you could definitely be woefully uninformed when the time comes. So, and these classes, and you guys being fourth year students and kind of on your way out, we want to make sure that you're up to date on all that as best as possible. And that'll be my job to deliver that message as we make it through this school year. So, all right, gentlemen, if you don't have any other further questions or anything, I bid you adieu and appreciate you, and we will see you in a couple of weeks. Have a great evening and stay safe out there, okay? Thank you.